Good evening, everybody. At last, we're ready to go. Apologies for the slight technical issues. How very embarrassing. But we're here now. You can hopefully all see the screen. Yep. Some of you I recognise, some of you I don't. So who's here for the first time tonight? Only two of you. Oh, well, I'm just not very good at recognising faces then. I thought we had more new members. But anyway, welcome. So you have jumped in on the second session of our second module. So we've covered quite a bit already. So I don't know if you have any sort of C++ or programming background. If so, then you should be able to jump in fairly easily. If not, then all of our material, except last week because I'm an idiot and I forgot, but all the slides for all the sessions we've done are available on our GitHub site, so github.com/cpplondonuni, and also almost all of the videos for the sessions that we've done, because we're live streaming them. We're doing so right now. We live stream all our videos. YouTube records them, and you can go back and watch those at your leisure. So that's youtube.com/cpplondonuni. I'd also like to say hello to Alex, who's a C++ programmer who's going to be helping us out, I hope, perhaps, who knows. But he's here to join us for this evening, so hello to Alex. Right, let's get on with it. First of all, the same thing I say at the beginning of every session, which is this feedback slide. So by now, most of you will have heard me natter about Slack many times. This is a chat application we use to, talk to each other in between sessions. Pretty informal. It's not run by us, it's run by another organisation, but we sort of piggyback on it. It's a CPP language Slack, so it's got a few thousand members, lots of different chat rooms on there talking about all different aspects of C++. But we have our own little room on there, it's #CPPLondonUni. So we encourage everybody to join that. You can go to that URL that's on the bottom of the screen, slack.cpp.al. It's got a little form on there, just pop your email address in. It'll send you a link to join us. And again, I mention this every week, but there's also a #learn channel on this Slack that has lots and lots of learners from all around the world and lots and lots of experts who are more than happy to answer questions. So that's, if you get stuck in any aspect of C++ and we're not around to help you, then #learn is a really great place to get your questions answered. All right. So last week, who was here last week? 5 of you. All right, well, if you were here last week, you would have had fun probably doing our little end of module questionnaire, which, that was, I'm sure, very enjoyable for everyone. After we'd got that out of the way, we went on to start talking about what this module is actually about, which is about custom types, defining your own types. Structs in particular, we might go on to talk about enumerations later, well, we will go on to talk about enumerations later, but we were introducing this notion of structs. So we're defining simple structs, creating variables, passing them to functions, all these sort of fundamental ideas. This week we're going to carry on talking about structs. We're going to talk about member functions, what they are, how you define them, why you want them, what they do. And we're also going to talk towards the end about const member functions. And again, what they are, why we need them, how you write them. So if you are familiar with the idea of methods, as they're called in most other languages, the first part of this session will probably be quite sort of, you'll be familiar with it already. Towards the end, the const member functions, this is something that's pretty unique to C++. So even if you think you know it all already, this might be a surprise towards the end. So just one note about the quiz results. Definitely not a test, all right? I mentioned that, right? It's not a test, not an end of module test, an end of module quiz, a questionnaire, just some questions that we ask you about C++, about what we taught in the last module, and then we give you a mark based on the correctness of your answers, right? Which is definitely not a test. Hopefully everyone who completed it now has their results. if you don't, come and talk to me or Ollie when he gets here. Oh no, he's not here this week, is he? Well, talk to me then, and I will sort it out. Sorry? Last week. Yeah. If you wish to take it and you haven't watched last week's video in which we went over the answers, then we can probably arrange that, but Ollie will need to do it because he's got the passwords and everything. So yes, hopefully everyone should have had their results emailed to them. If you haven't, then let me know. Overall, everyone did really, really well. Nobody got full marks, but that's because Ollie's evil and asked really hard questions. But a number of people got very close. And overall, everybody did very well. So very, very well done to everybody who took that. Personally, I'm very pleased. And you should be heartened as well because, it means you really took on board the things I was wittering on about for 6 weeks. So, yes, well done. If you have any questions about it, if you missed it and want to take it, for example, we can arrange that. If you have any questions about your answers, if you are, you're disputing it, you think you deserve more marks than Ollie gave you, come and speak to me, or, well, I forgot that Ollie wasn't here this week, but he's the quiz master, but yeah, come and speak to me and I'll see what I can do. Any further questions about the not test? It was session 1, but I haven't put the slides up online despite numerous people nagging me because I'm an idiot. So I will do that, I promise. But the quiz wasn't actually in the test; it was a separate thing. But well, if you watch the video, then we went over the answers in the video, so that might give you a bit of a clue as to. Yeah.
Given the questions that Christian failed, you did score well. At least failed those.
Yeah. All right, so I left you with, it was actually pretty, it was more a class exercise that happened to occur at the end, so I made it the homework. Much to the disappointment of Saad, who wants me to give you really hard homework every week, so that's what I'm going to do from now on. You can all thank him. So what I asked you to do, at the end I said, basically a bit of practice defining your own structs, which was what we were introducing in the last lesson. So create a struct called student, give it a couple of member variables, and then write a function that takes a const reference to a student. And then, towards the end, the last one actually, create a vector of students as well. So the whole point of this exercise really was to demonstrate to you that using your own struct works exactly as with built-in types, what we call fundamental types, things like ints and floats and bools. Right? Once you have defined your own type, you can use it pretty much exactly as you use built-in types. So have a quick look at the solution to that. Oh, line by line apparently. So it's a little bit tiny for those at the back. You can squint, or there are a few seats at the front if you want to move closer. But here we've got our struct student. So we use the struct keyword to introduce this. This class, this struct, has 2 member variables. In this case, they're both of type standard string. They're named first name and surname. And we've given them both defaults of an empty string. That's what the 2 double quotes mean. So that's our type definition, our struct definition. Now, I've defined a function that takes a student, this type we defined, takes a student as an argument. So print surname returns nothing. The argument type is a reference to a const student. That is, it's a read-only reference to a student. And as you can see, all it does is print the surname, which, you know, the clue is in the name, I guess. So in our main function, we can, of course, create an object of type student, or in this case, type const student. So this is an immutable instance of a student. We can't change it after we've created it. The variable is called Tom, and I've initialized the first name to the string Tom and the surname to the string Breza. Because I lack inspiration, right? I can't dream up new names, so there we are. So now I can pass this variable that we've defined to the print student function. Sorry, to the print surname function. And this will, as you might guess, print Breza. We can also create a vector of students. So just as we can create a vector of ints or a vector of floats, we can create a vector of our type that we defined. So I've created a vector of type student, and I've called that vector students. And now I'm just showing off a few ways in which we can initialize the members of this vector. So for the first member, I'm copying this Tom variable I defined earlier. For the second one, I'm just directly initializing a student with the first name Ollie and the surname Din.
So how does we know that the second one actually is of the type, it's not something else?
Because we've said what type this vector holds.
Yeah, but the second line does not specify any type.
No. This is what we call an initializer list, this second entry. But the vector knows it is expecting to be populated with students.
So just on that then, because it's matching the same arguments as expected,
Yeah.
that's what actually then says that's fine to be accepted. But if you were to actually have a list of 3
Yep.
or just 1, what would happen then? Would it bug out then because it's not actually?
No, you have specified the type
Yeah.
that you want the vector to contain. So that's in the angle brackets here.
Yeah.
So for now, for a simple struct like this, what we call an aggregate type, you can just supply it in these braces. You can be explicit, as we are in this third one, and say, no, I am definitely creating a student. But in this second case, I actually probably put these two the wrong way around. Should have demonstrated it the other way first. But we can be explicit, as we are in the third line. Something's gone a bit funny with the syntax highlighting there, but never mind. We can be explicit, as we are on this third line, or we can actually just omit the word student because it knows what type is expecting the vector to hold. Sorry?
It's implied.
It's implied. It's implicit, yeah. If you put Ollie in curly braces, that would actually be okay. Yep. Forget about constructors for a minute. Okay, we're not using any constructors for this. This is something called an aggregate type. So we're going to get on to talk about constructors perhaps next week. But don't worry about constructors yet. This is what we call an aggregate type. So we can just directly initialize all of its fields. Right? If we supply fewer initializers than there are members here, it will use this default initializer. So if we didn't say Ollie Din, or let's use the bottom one, if we didn't say Tristan Brindle, we just said Tristan, then the first name field would be initialized to Tristan, and the surname field would be the empty string. Does that make sense? A few nods, but Lauren's looking quizzical. No, it would be an error.
In this case,
And Brindle is the surname, yes. Yeah. Yeah. So it initializes the members in the order that they appear in your struct definition.
Before that, we need to write the include an iOS string.
So yeah, at the top, I have left this out because it's already quite a lot of text on the slide. But at the top, imagine there's hash include IO stream and hash include string that you'd need for all this to actually compile. So we defined our vector of students. And then we can use this range for loop that I showed off a few weeks ago to iterate over all of the elements of this vector, 3 elements in this case. So this is going to loop over every element in the vector, and it's going to call print surname for each student in this vector. So notice this argument type is const auto ref. So we're not copying each student, we're just taking a reference to the vector element. We're allowing the type to be deduced automatically, that's what the auto keyword is doing. And const means that we can't modify the elements inside of the for loop.
What did you say auto did again?
So auto is for type deduction, right? So if you're familiar with C#, it's kind of like the var keyword in C#. So you can use it to introduce a variable, and it will deduce the type of that variable from the initializer. So
is that something similar to using object in Java?
No, because object sort of like kind of erases the type, whereas this
It's more like type inference.
it's exactly type inference. Yeah. So if I said auto I equals 0, then I would be deduced to be an int, because a literal 0 is an int. So it's going to look at the type that's on the right-hand side of the equals and go, okay, that's an int, therefore I must be an int. Yeah. Okay, so hopefully a few of you had a go at that. And hopefully it made sense. If not, then, well, I'm very, very quickly going to go over a little bit of what we were talking about last week. So if you weren't here, this is just a little bit of revision. So pretty much every programming language or every non-silly programming language under the sun has some notion of structure type or a record type or a class type, some collection of variables that we can treat as sort of one whole unit. Right? In C++, we call this a struct, a structure, data structure, struct. C++ also has classes, as do many other languages. C++ is kind of unusual in that classes and structs are exactly the same thing. Right? This is quite different from if you've done C# or Swift or D or whatever. Those work quite differently. Classes and structs in those languages work quite differently. But in C++, they work in exactly the same way. The only difference between a class and a struct are a couple of the defaults that you get when you first define your class or struct. Right? So everything you can do with a struct, you can do with a class, and everything you can do with a class, you can do with a struct. They are the same thing. So I'm going to be using the struct keyword just because for the things we're doing for the next couple of weeks, that provides the better defaults. But I will probably quite often slip and talk about defining a new class or class types. What I mean is structs. When I say structs, I mean classes. When I say classes, I mean structs, because they're the same. Right?
Why is it called struct?
So struct is short for data structure, and it's terminology that came from the C language. So C++ inherited, or started off anyway, as a lot of extensions to the C language, which is an earlier programming language, still widely used. So struct comes from that. Then they added this class keyword as well, which actually is kind of pointless, but you know, it's been there for 40 years now, so we can't really get rid of it. In C++, a struct or a class is a collection of data members, which we call, in the C++ terminology, we refer to these as member variables. Other languages, they call them fields. This is the actual data that the struct contains. And in C++, that we'll talk about in a couple of minutes, we can also define member functions, what other languages call methods, that operate on these member variables, typically anyway. And as we just saw on the last example, we create a new type, a new struct type, using the struct keyword. And as I just mentioned, unlike some other languages, struct and class mean pretty much exactly the same thing in C++. And it's just a couple of defaults that differ. And again, I will probably slip and talk about classes. When I do that, just mentally change it to structs, because, yes?
Without obviously diving too deeply into it, but when you talk about like the defaults that you get,
Yes.
that are different, is that like talking about where if you've got some data members in a struct versus in a class, some of them may be initialized to like null, or some of them may be initialized?
It's nothing to do with initialization. If you really want to know the difference, there are only two differences between class and struct. This is like a spoiler for a couple of weeks' time. Yeah, is that classes default to all your members are private by default, unless you override. In a struct, all your members are public by default, unless you override. Right?
Cool. Yeah.
But we haven't really got onto private and public data yet, but that's like next week. Yeah.
I've also seen like in the wild that they are used to express like different things. That a struct, for example, you would use when you want a plain old data type. And with a class, you are trying to express the concept of like a class, like an object-oriented.
Yeah, so that probably didn't come out on the microphone, but the point was that although the keywords do pretty much exactly the same thing from the language point of view, many C++ programmers use the two words in a sort of a slightly different sense. They use struct when we've just got what we call plain old data. That's a type with only public members, perhaps with no constructors, doesn't use accessors, no invariants, basically, is what we're talking about. And they'll use class to signify perhaps a slightly more heavyweight thing, perhaps polymorphic, perhaps with private data, invariants that we need to maintain. Yes, that is true. That is widely done. Personally, it's not a style I tend to follow. I just use struct for everything because, well, why not? But yes, that is something you'll often see. And it's also the reason I've started off with struct, because all of the types we're using, at least for the next week or two, will be these sort of lightweight, plain old data type things. So we use the struct keyword to introduce a new struct, a new type. Here I've written one that's called point. So this struct point has two members named x and y, two member variables named x and y, both of type int. And I've supplied default initializers for these, which initialize both of them to 0. The initializers are optional, but particularly for built-in types like ints, it's good practice to provide them, because otherwise sometimes you can get into a situation where your members aren't properly initialized and they just contain junk. So particularly for built-in types, it's good practice to put these default initializers in, initializing them to a sensible default, such as 0 for an int. One thing to remember, and again, this is a bit different from other languages, and is something I forget to do on a daily basis, is that a struct definition must always end with a semicolon. That's supposed to be a semicolon, and it was a semicolon, but Keynote is silly. Let's see if I can make it appear again. There we go. See, it's a semicolon now. Your struct definitions always end with a semicolon. If you don't do that, 95% of the time the compiler will just remind you and say, oh, I think you meant to put a semicolon there. Very, very occasionally, you'll get a sort of funny situation where you'll get something that is almost but not quite legal C++ code when you leave off the semicolon, and you might get a really weird error message. Like, honestly, this is something I forget all the time. It's kind of annoying, but those are the rules. Always put a semicolon at the end of your struct definitions. The other thing we talked about last week is accessing the members of a struct. So, much as in other languages, if we have an instance of a struct that is an object, say, of type point, named P, we can access the X and Y members of that object using the dot. So, if we had a point named P, then we could access the X member by saying p.x. And probably no surprise, we could access the Y member by saying p.y. Yes?
Can you initialize the members at the start, or can you leave them blank, or what's the best practice?
What's the best practice? The best practice is always make sure your members are initialized.
So what if you don't know what you need to pass then the value? How would you initialize?
I'm not sure what you mean.
Say you're going to pass a value to a function to store in.
Like an out parameter?
Yeah.
Well,
I don't know, like in the previous example, there's name, right?
yeah,
And you're passing your first name and let's say
yeah,
at the start you don't know what that is, so you just put in an empty space.
exactly, yeah. Yeah.
But what if you just left it as int x without the assignment? What happens at that point there?
Okay, so this is where C++ gets kind of complicated, right? Because C++ is all about efficiency, sometimes to the detriment of other things. So if you imagine we had like an array of 1 billion points, zeroing all of those, we knew we were going to overwrite them later. Zeroing all of those would take some time, right? So C++ kind of gives you a way of avoiding that, like zeroing happening by default. A lot of people don't like that. A lot of people think it's quite dangerous behavior. So the recommendation is, well, if you give them these default values, then you can ensure these are always initialized, right? Otherwise, what might happen is these numbers will just contain whatever junk happened to be in that bit of memory at the time, right? Which is bad. It's actually worse than that, but you know. The moral of the story is make sure things are initialized and you'll never go wrong. Spacecraft crashing into Mars. No, that was about units. Like one team at NASA used feet and the other one used meters or something. Or miles per hour and meters per second. I can't remember, but it was to do with units. One thing to note, if you're coming from other languages where they do this differently, is that when we introduce a new struct, like our point on that previous screen, that always introduces a new type. Two structs with different names are always different types, even if they have identical members. Right? C++ is a pretty type-safe language, so even if two structs have the same name, have the same members, we can't use them interchangeably. This is actually a really good thing. But it's a bit different how some programming languages work. So that's the reason for this little bullet point. As we saw with the exercise solution a few slides ago, we can declare variables of struct types, just as we do with built-in types, fundamental types as we call them, like ints and floats, right? We just declare the type, the variable name, and the initializer. And again, as we saw, we can pass these variables to functions, just as we can with ints, floats, whatever. And there's one thing to bear in mind, is that C++, as I have droned on about for many of these lessons now, uses value semantics by default. So that means unless you do something special, when you pass a variable to a function, that function will receive a copy of the data that you give it. Right? So any changes that the function might make to that variable will not be reflected in the original, because the function is operating on a copy. This is what we call value semantics, or pass by value. So by default, the arguments we supply to a function are copied. This can be a problem in some situations, right? If we've got a vector of 1 million strings, that might be several megabytes of data. We don't want to copy that every time we call a function. That would be really inefficient. C++ is all about efficiency. So we can optionally use pass by reference instead. And to do that, we add this little ampersand to the type name to specify that, okay, this particular function parameter is a reference type. So that was what we saw with that print surname function on the last slide, a couple of slides ago. So just as we did with ints and floats and strings, etc., if we have our own custom type, we can pass it by reference to a function if we want to. We can use a const reference, one of these read-only references that says, okay, you can look at this, but you can't change it, right? Const references are brilliant because they are a promise, guarantee that you cannot, that the function you call will not modify the argument that you give it. The compiler will prevent you from doing that. It's a very similar example to the one we just saw. This time we've got a struct called example, again, because I'm not very good at naming things. We've got a struct called example that has two members. Again, this time it's got a string member called str and an int member called value. And again, I've given these default initializers. Then I've got a function called myFunction. Again, suck at naming, sorry. This function takes as its argument type a reference to a const example. That is, it's a read-only reference to an example. And this function returns type example. But remember, value semantics in C++. This means that although we're not copying when we supply something to the function, we are copying on the way out. Right? Because we're returning by value. It's not returning an example ref. Well, in fact, it couldn't, but it's not returning a const example ref. Right? It's not returning a reference. We're returning a value type. Right? So this function is going to copy whatever you give it back out again. So we can create a variable of type example. Here I've named it ex1. And I said, okay, ex1 equals curly braces, and then we've initialized the string member and the value member. In this case, with the string a and the value 1. Unlike in C, we're allowed to omit the equal sign. And in fact, just out of force of habit, this is how I tend to write most of my variable declarations. So that's probably what I'm going to be doing from now on. We can omit the equal sign and just have the name followed by the curly braces.
When we say like that, you're declaring a variable.
Yep, these two have exactly the same meaning, ex1 and ex2. They're declaring two different variables, but they're both variable declarations.
I'm used to seeing a variable declaration by having like the equal sign.
I know, C++ is a bit weird. Oh, sorry. Trust me, I am trying as hard as I can to make variable initialization as simple as I can, but as Alex would probably agree, it gets a lot more complicated than I've let on so far. All right, so on this third line for ex3, well, first of all, we're declaring a const example. This means it can't be changed after we've initialized it. But I've supplied no member initializers in here. So what's going to happen is it's going to use these default values that we wrote in our definition up here. So the str member of x3 is going to be default, and the value member is going to be -1 because we didn't override them there, so it's just going to use these default values up here. Does that make sense? I've got a nod. One nod.
I'm confused at the last bit. Where you've got the example 3.
EX3, yeah? Well, first of all, the const is a bit of a red herring here. Just ignore the const for now. Right? So if it just said example EX3 equals empty braces, right? Okay, so imagine we just said this. What this is saying is I want to declare a new variable named ex3 of type example, and I'm going to supply no member initializers of my own. That means that I want you to use the defaults that the class supplies, the struct supplies. Yeah? So if I had said x3 equals, and then I supplied hello and 4, this would initialize those two members to hello, the string hello, and the number 4. Right? Well, I can optionally leave that one out and only supply one initializer. And in that case, this first member is going to be initialized to hello, and the second one is going to have its default value of -1. And I can go one step further and remove that one as well, in which case both of them are just going to use their default values. And then I can go one step further, and well, we don't actually need that equal sign, so I can leave that out. And then, well, we like to declare things as const whenever we can. Right, it's a really good tip. Whenever you can make something const, do so. That is, whenever you know it's not going to change after initialization. So we can write that this thing is immutable. This thing can never be changed after we've initialized it. We declare it const. It's constant. So we say const example ex3 with using the default initializers. right?
Does that mean that the const that you use there is constantly, you don't necessarily have to?
You don't have to declare it as const, no, right? So it would be perfectly fine to say that. The difference is that if there's no const there, then I can go and modify ex3 later. I can go and change the str and the value members later. But if I write const in front of it, that means that it can never ever change after I've initialized it. Right? It means it's immutable. So I don't know if people can see this at the bottom. This line is auto ex4 equals my function brackets ex2. So what's going to happen here? Well, first of all, we're going to call my function up here, and we're going to pass it ex2, which we defined earlier. So this is going to create a copy of this guy, ex2. Can everybody see why that copy is occurring? Because we're taking in a reference, but we're returning by value. That is, we're returning a copy of the thing we got.
Because you've got that auto there as well, it notices that there's a type of example there.
Precisely, right. So this auto ex4 says, okay, I want you to create a new variable for me of type ex4, but I'm going to deduce the type from whatever this function returns. So we know this function returns a type example. So ex4 is also going to have type example. Right? This is type inference. Right?
What would happen if you're returning a reference to example?
If you return, then right. So this is what. So
So it's like it will be exactly the same as
it would have exactly the same effect, right? Because auto never deduces to a reference type unless you specifically ask for it. Like I say, C++ really values semantics by default. You only, or most of the time, you only get references. In fact, I think with one exception, you only get references when you specifically ask for them. Otherwise, things are values, right? So had we said auto ref, yeah, oh well, it would actually give you an error in this case, but yes, it would try to create ex4 as a reference to some example object. Yeah,
So if the ampersand next to example stops it from making a copy of the object,
here, yes.
why is it after the type instead of the instance? Is there a difference between the two?
So you could write this as const example space ampersand ex.
I don't understand. Because if it's to stop you from making a copy of ex,
Yeah.
then how come the ampersand isn't after ex and instead it's in front of after the type?
Okay, so conceptually, this parameter named ex is of type reference to const example, right? So the type of ex, it's a reference type. Okay, so it belongs as part of the type name here. Now, as it happens, C++ is not particularly fussy about white space, and it doesn't really care whether you write this attached to the type or whether you write it attached to the variable name, the front of the variable name. And some people have for some reason that I don't understand, prefer to write it attached to the front of the variable name. Yeah, that's not me personally. I see that as, you know, conceptually part of the type name, so I always write it like this, as do most people. But very occasionally you'll see it over the other side, which is a style some people prefer. Okay, so ex4 is going to be deduced as having type example because that's the type that the function returns. And the member ex4.str is going to be, ooh, what do people think it's going to be? It's going to be the string containing B, yes. And the ex4.value member is going to be, I heard the correct answer, I don't know who said it, but yes, it's going to be 2, because all that my function is doing really is creating a copy of the thing that we gave it, which was this guy, ex2.
So because it's modifying it by value, right?
It's returning by value, yeah.
Return by value. EX4 is in effect a distinct copy of EX2. So if you were to change EX4's str value to something different,
Yeah,
EX2 remains unaffected by that.
that is absolutely 100% correct, yes. Well done, yeah. So ex4 and ex2 are completely distinct objects, right? So again, sort of dived quite heavily into this in the last module, but a good way to think of it is like when you create a copy of like a Word document on your computer, right? When you create a copy of a variable in C++, anything you do to the copy doesn't affect the original, right? So it's like you create a copy of a Word document on your computer, you edit the first one, well, the copy doesn't change. It's exactly like that. That's the essence of the value semantics. And again, it's a bit different to how some other programming languages work. But in essence, what it means is that by default, the types you use in C++ behave like fundamental types do, behave like ints do. Right? There's a saying for C++ programmers for how to write good types, which is do as the ints do. All right, let's talk about member functions. So we've just seen that that structs have data members, what we call member variables, called fields in some languages. This is the actual data that the struct contains. So each instance of the struct, each object of that type that we create, has its own copy of this data. Right? We can also define what we call member functions. So we've seen that, in fact, just on that last slide and through this whole course, we can define functions that don't belong to any class. These are what we call non-member functions, ordinary functions, normal functions. The C++ terminology, we sometimes refer to these as freestanding functions or just free functions. But actually, C++ has 2 kinds of functions. It has these freestanding ones, which are the ones we've seen so far, and it has member functions. These are functions that are associated with some type. And a member function operates on an instance of that type. So, as I say, most other languages call these things methods. If you're used to Java or C# or whatever. I'll probably use that terminology from time to time as well. Properly, they're called member functions. I will sometimes say method, but when I say method, I mean member function. Just a note for any Java programmers in the room who are sometimes a little bit surprised by this. C++ methods, member functions, are not virtual by default. That is not overridable by default. In Java they are. C++ they're not. You have to use the virtual keyword like you do with classes in C#. So, if you're not a Java programmer, just ignore this last bullet point. We're going to talk a lot more about object-oriented programming and inheritance and virtual functions and all that fun stuff much later on, or not much later on, a bit later on in the course in the next module, if all goes to plan. So yeah, if you're not a Java person, just ignore that last one. So we can write functions that are associated with some type. Member functions, functions that belong to a type. Well, we've just seen we access the members of a struct, of a class, using this dot. We write the instance name dot whatever. And we use the same notation for calling member functions. So for example, here I've declared a variable called str, again, of type string, standard string. Well, standard string is a class type, struct, and it has member functions. It has lots and lots and lots of member functions, actually. And in particular, it has one called length, which returns the number of characters in the string. So what we're saying here is, okay, I want to call the member function named length using on this string instance that I have. I want you to return the number of characters in this string, please. So it's going to return 11 in this case.
That's what I find a little bit confusing, probably because when you're doing something in another language, is when you go auto equals string.length, I would have just gone str.length and it would have given me the same thing.
Oh, right. So, yeah. Let's make it appear properly again. Okay, so I'm actually doing two things on this last line, right? I'm declaring a new variable called len. Okay, so basically this is the member function call. This returns the number of characters in the string. This returns the number 11 in this case. And then I am capturing that in a new variable called len. So yeah, that bit, str.length, empty brackets, that's the member function call. And then this is going to return a number, and then I'm just capturing that number in a new variable. So sorry if that was a bit confusing. Yeah. Because otherwise we're just going to ask for the length and then do nothing with it. So it was kind of pointless. So I wanted to kind of demonstrate, that member functions can return values, just like ordinary non-member functions can. And we can capture those values. So yeah, str.length calls the length member function on our string instance. Right, so this is the important difference between member functions and non-member functions is that member functions operate on an instance of the type. Right? Some languages, they call this the receiver object. It's the object we're operating on. And in this case, as you might be able to guess, the length member function returns the number of characters in the string. It just so happens that I picked a member function which took no parameters. But just like ordinary functions, freestanding functions, we can supply data to a member function. So to pick another member function of string as a member function called resize. Again, this does something you might imagine. It resizes the string to the given number of characters. So in this case, I'm saying, okay, resize yourself to 5 characters, so it's going to chuck off everything after the O. And it's now, if I called .length afterwards, it would be 5. It would return 5. So a way that you can think about member functions, if you like, is almost like you're sending a command to the object. Right? So this first one that's kind of half erased itself. You're sending a command to that object saying, tell me how many characters you've got. In this second example, you're sending a command to that object saying, okay, resize yourself to this number of characters, please.
How would you use that? I'm on, I don't know if it was three or something when we went through vector,
Yep.
like using that in an array. How would you do that? For this similar example that you've got. Because when you go str.length, then it gives you the number of characters
Yes.
that's actually in there.
Yeah.
But what if it was like a vector and you had like multiple different words in there, rather?
Okay, so what if you had a vector of strings?
Yeah, vector string, yeah.
Then you might use like one of these range for loops to operate, to iterate, to loop over every string that was in that vector, right? And then for each individual string, you could call the dot length member function.
Oh, so you'd have to do them individually?
Yeah.
But if you call a vector dot size, you get the number of elements in that vector.
Yeah, so vector itself is a class type. It has member functions. Vector has a member function called size that tells you the number of elements in that vector. So you might have seen me use that example as well. Yes, we'll talk about that in a little bit. So you can think of member functions, if you like, if it helps, as almost like sending a command to that particular object. A command to resize yourself, a command to tell me how many characters you contain, right?
Sorry, just quickly as well on that, just kind of noting that the way to almost identify the difference between a data member and a member function, because you're using dot notation effectively to
Yep.
access it, is that the function has the parentheses at the end, irrespective as to whether or not you pass any kind of arguments to it. Is that right?
Yes, yeah, correct. If you want to call the function, you use you have to have the parentheses, even if you're passing no data. So how do we write our own member functions for our own types? Well, we do so in a very, very similar way to how we write ordinary non-member functions, except that we write the function definition inside the struct definition, right? We nest it inside. So here I've got struct rectangle, contains two floats named width and height. And now I'm declaring a member function called getArea. So if you didn't know anything about this struct business up here, this would just look like a normal function definition, right? Except that because it appears within a struct definition, it's a member function. So this is a function that takes no other parameters and returns a float. And well, to calculate the area of a rectangle, it's the width times the height. So we can just return width times height. So remember remember that member functions operate on an object, right? So we can refer to the member variables of that object from within the body of the member function. Somebody is going to call like rect.getArea, and then width and height within the body of this member function refer to the members of that object. So in Python, for example, this is explicit. You'd write, like, usually it's called self as the first parameter of your method, and then within the body you'd refer to self dot whatever. In C++, this is implicit, right? The object, in fact, it's technically called the implicit object, right? This is sort of passed, in fact, literally passed as a hidden object, as a hidden member of your hidden argument to your function, right? So getArea operates on a rectangle object. We can refer to the member variables just by using their names like this. We don't have to say self.whatever or this.whatever. And this bullet point just says exactly what I've just said. Because I'm that good, I knew what was coming.
What if I just wanted to know the width and I didn't?
Then you could just write, rect.width. Yeah.
That would give me
Yeah, because we can access member variables just by saying like .name.
Is there any particular advantage of just having void and having another variable, say area, and then just width area equals width times?
So I'm not quite sure what you mean.
If you have a member function returning void,
Yeah.
you have another member variable, say area,
Mm.
and then you have void return get area, and it's area equals width times void. It's like
Okay, so what you're saying is you would have a third member variable named area, and that this would be like blank or 0 until you called getArea. Right. Well, I mean well, would it? Right. So what you're saying is, let's put that example back on the screen. So we'd have right, so now we've got 3 member variables. And then we're going to write a member function returning void. Let's call it calculate area, because it's not getting anything, we're not returning anything. We're going to call it calculate area. And then this will set area equals width times height. Okay, first of all, this will work. This is, 100% valid C++. Can anybody see a disadvantage to doing it this way? Yeah.
you have to call that function first before you're able to work out what the area is. Whereas if you've got it as a function, and if somebody wants to then change the width or the height of that particular rectangle, then you have to remember to calculate the area thereafter.
Yep.
Additional step up.
Yeah, so that's one disadvantage of this is that the area, calculating the area is now, or getting the area rather, is now a 2-step process. First we've got to calculate, then we've actually got to get the thing. And because all these fields are public, so if somebody changed the width or the height, we'd have to remember to call calculate area again to recalculate this guy.
It's always killed after the variable is killed once the first curly brace closing is breached.
What?
So we're getting here,
Yeah.
so the area is being created.
No.
Also this
No.
one.
It
Okay.
refers to the member variable. So
Okay.
yeah. It worked. Yeah, this just defines the function. You like to actually call it. I'm going to write it in a different color. Just imagine this is like a completely separate bit. So we'd have like rectangle rect equals, I don't know, like 3, 4. And then we'd say like rect dot calculate area, and then we'd like do something with like print. I'm just going to pretend we've got a print function. So we do something like that. Need my semicolon. Right, so that's how we'd use this. Right. There's another disadvantage to this, which can be quite important. Memory, yes. So previously, our rectangle just had 2 members, 2 floats, 4 bytes, so rectangles 8 bytes. Now, our rectangle is going to have a 3rd member, 12 bytes. Well, it's probably not actually going to be 12 bytes. The compiler likes powers of 2, so it's probably going to bump that up to 16 bytes. So we're going to, be using potentially a lot more memory. Now, this might still be a valid approach to use in some situations. Calculating the area is like it's a trivial thing to do, right? It's one floating point multiplication, right? It's more or less free. If this was something that was very long-winded to compute, if it had to go off and this calculation took a few minutes to do, well, perhaps you wouldn't want to do it all the time. It would make sense to sort of do it once and then save the result and only recompute it, like particularly when you needed it. And in that case, perhaps this might be a valid approach. But in general, I would say because this is this is a trivial calculation, that the original approach of saying get area would be the one to go for. Anyway, that was a fun little diversion for a couple of minutes. Yeah, where were we? Oh, we were talking about member functions, weren't we? Well, instead of rectangles, let's talk about circles. I'm just warming you up for the object-oriented programming class, where I'm going to introduce All right, so we've got a circle. It's got a radius. Floating point radius. And again, we can add a getArea member function to our circle. If you remember from maths lessons way back when, formula for the area of a circle is pi r squared. So it's this m pi, that's just a constant that the C standard library gives us usually. It contains the value of pi, 3.14 whatever. So pi times the radius, that's going to give us the area of our circle. We can define a second member function. This one I've called resize. So again, you can think of these as a bit like commands that you give to an object. The first one says, okay, tell me what your area is. Calculate that for me, please. That's inquiring as to something. Right? The second one is actually telling it to do something. In this case, resize. Resize yourself, please. So we've got this float factor. So we can imagine we might want to make the circle twice as big, the radius twice as large. So if somebody supplies us with a factor of 2, we're going to multiply our radius member variable by 2, multiply the value of the radius by 2. So I'm going to create an instance of our circle class named C1, and I'm going to initialize the radius to 2. And then I'm going to print the area of this circle. Right, really quickly, can anybody tell me what this is going to print?
13-ish.
It's not bad, actually. 12.566-ish. So yeah, well done. Yeah, so this is going to calculate pi times 2 times 2, which is, 12.5-ish. Then I'm going to tell the circle to resize itself. I want you to scale your radius by, in this case, 0.5. So I initialize radius to 1. Now I'm telling it, okay, scale yourself. So after this member function, after I've called this member function, this method, radius is going to be 1. Make sense so far? Yeah, good. And now I can call getArea again, and it's going to return. Come on, you're good at this. It's going to return pi this time, right? It's going to return pi times 1 times 1, which is going to be, 3.1415926. I'm just repeating digits now, etc. So 2 key things from this slide. Honestly, I forget 1 week to put the slides on, and suddenly everyone's like photographing every slide because they don't trust me anymore. I'm sorry I let you all down. I'll be better, I promise. Anyway, right, 2 key things from this slide. First of all, we define member functions, we write member functions. Sorry? By writing them like a normal function definition, writing them in the class. Within our struct definition, we write our member function. Within the body of the member function, we can refer to member variables of the object on which this function was called. So this is how we define member functions, and this is how we call member functions. We just say object dot function name, and then with arguments if the function takes any arguments. This one doesn't, this one does. But either way, we need to supply the empty brackets. Does that all make sense? Good, because you're going to have a bit of practice. Oh. Silly me. That's better. So, we're going to go back to our old friend point. So we need to write a struct name point and then add a couple of member functions to it. One named equal to, and then after that, a second one named not equal to. So basically, just do what you saw on the last slide, but for yourselves.
That's if you've got a picture of it, because I can't remember.
Okay, so I'll give you a little while to have a go at this. We did have a bit of a delayed start, so I can't give you as long on this as I might like. But hopefully you can all have a bit of a crack. And in particular, if you get there, have a go at the last bullet point and tell me what happens. Don't be water. Yeah, but the Okay. I couldn't quite give you as long as would be ideal. As I say, lost quite a bit of time at the start due to technical things, so sorry about that. So quite a few people managed to have a good go at that, I think, walking around. Who managed to do everything? A couple of you. Who managed to do some of it? Some of it.
I did
Most of it.
apart from the last minute.
Okay. Let's have a look at a solution to this. There are a few ways of doing it. This is my solution. As you can see, it's quite long, so I've split it onto two screens. First of all, don't worry about that CSRT bit for a minute. That's going to, you'll see what that does in a second. So we're going to define our struct points. I think pretty much everybody got this as I was walking past. So this is point is a struct with two member variables, an int x and an int y. Now we're going to define our first member function equal to, and we're going to take an other point as a parameter. So remember, we've got 2 point objects in play here now, because equal to is a member function. So we have an object that we're operating on, the implicit object, and we have this other point that we're being supplied as a parameter, which I've handily named other. And what we want to establish is whether these are, in fact, the same value. The way we do that is to say, well, if they have the same x-coordinate and the same y-coordinate, then they point to the same, they represent the same point on our graph or on our screen or whatever. We can do this a few ways. We can, I don't know, set up a couple of Boolean values and test those. We can have a couple of if statements. You can actually do this, if you really fancy, just in one line. So we can say, is our x, that is the object that we're operating on, is our x equal to others' x-coordinate? Remember, when we're testing for equality in C++, we need to use this double equal sign. So is x equal other.x is our x-coordinate on the object we're operating on. Is that equal to the x-coordinate of this other guy? And is our y-coordinate equal to this other guy's y-coordinate? And if both of these things are true, if this is true and this is true, then the function itself will return true. If either of those things is false, then this function is going to return false.
What would happen if you use one ampersand and, sorry, character?
So the single ampersand represents a bitwise OR, so that's not something you want to do. This represents a logical OR, which is like 99% of the time what you want.
And easier to understand.
Yeah. So the second part, or the slightly later part of the exercise, was I wanted you to define a second member function called not equal to. Well, this one's pretty easy once we've got the first one. We can return not, exclamation mark, given a Boolean inverts that Boolean, not equal to.
Would it be better to actually write your own definition?
No, it wouldn't.
I'm just asking, because if you modify the first one for whatever reason,
Yeah.
that would have an impact on this one.
Yes. But you always want equal to and not equal to do opposite things, right? You always want them to return. Yeah. No, please.
No, I was going to say, so I initially did it that way.
Yeah.
And I sort of doubted myself, and I put like used a logical or instead, the two bugs.
Oh, up here.
No, in the bottom one, not equal to.
Oh.
It basically said that if x was not equal to other
Dot x.
or
Or, yeah, so if you were to write that out longhand, that would be exactly the way to do it. this is a sort of shortcut way to do it. So say, well, we already know how to say whether the two things are equal. So all we're going to do is invert that Boolean. Yeah.
When it's getting compiled, the compiler can see both functions.
Yeah.
So he will probably in the end turn the second function into what you've written by him.
Yeah.
Right, okay. That's part of the compiler optimization, right?
Yes. So this what it does, what it calls function inlining. So it can see the definition of this function, and it can just directly substitute that. So, yeah, this is going to be no less efficient than if you wrote it yourself. But what I wanted to demonstrate just with this is why I wrote it this way. In fact, why I asked you to write a second member function, because I wanted to demonstrate that you can call another member function from within a member function, if you see what I mean. Right. So this member function can call this member function on the same object. Member functions can call each other. So that was really the point of this second member. In fact, no, it doesn't. So C++ inherited from C this sort of weird thing that you normally have to write functions, like declare functions before you call them. Within a struct, the rules are slightly different, and like we could basically swap those around and it would still work. So this is the definition of our struct point, and it's two member variables, two member functions. And then we're just going to have a few tests for this. So we're going to create a variable of type point. It's called p1. We're going to set x equal to 1, y equal to 2. And then this is a good check. Is a point equal to itself? We hope so. And yes, it is. So this asserts keyword. So assert is really, really useful for doing simple tests. Things like this. Right? What assert does is when you have a debug build of your program, that's what you get by default in C-line, assert will check that this thing, it expects a bool result, and it will check whether this is true. And if it's not true, it will crash your program and say, hang on, you failed this assertion on this line. And it will give you a little link you can click that will take you to the exact line that failed. Right? This asserts that this fact is definitely true. So it's like a very blunt instrument, and it doesn't replace like proper testing frameworks and stuff like that. But it can be useful just for kind of simple, relatively simple things like this. So again, part of the reason I'm demonstrating this is because this assert tool is really useful for ensuring things are true and crashing your program with an error message telling you exactly what failed otherwise, or exactly the line that failed anyway. All right, so now let's define a second point P2 and assert that P2 or P1 is not equal to P2. And we can spell that two ways. We can either use our equal to function and then invert the result, or we can just use the not equal to member function, which does exactly the same thing, at least in my formulation. Yeah.
That assert itself, that function knows whether you should be in.
So assert only knows about bools. Right? It expects a Boolean condition, and it expects it to be true. And if it's true, that's fine. Your program will continue, and nothing will happen. If it's false, it will terminate your program. Yep. So now we just declare a third point with coordinates that are different from either of the other two. Assert that this one's different to the other two as well. And now we get to the interesting one. This was the last bullet point. Somebody got to anyway. I declared a point P4, only I've declared that this point is immutable. It is const. This cannot be changed. So now I'm going to say P1 dot not equal to P4. Right. P1 is not equal to P4. Everyone agreed? This is going to be fine. It's going to work. All right. What about now? So all I've done is swap around P1 and P4. P4 dot not equal to P1. What's going to happen? What did happen if anybody tried this? I know one person did.
Logically says it should say is true, it's not equal, but I suspect it's a trick.
It is well spotted. It is indeed a trick question. This,
Because you want to apply constant method of
you've been doing this too long, Lauren. This last guy here is going to fail to compile. The compiler is going to give you an error message. It's going to refuse to compile this program, which is kind of weird. Because if you take away this const keyword, then it works okay. You know, if you take away the const keyword, then it's just what we've done 3 times already. So this const keyword is doing something strange.
It makes sense if it was modifying inside the function.
Well, you're going to make me like reveal this line by line again. It'll last longer. Moving on in 3, 2, 1. Okay, so const member functions. That was what that last bullet point was leading us on to. What? So, within a member function, we are allowed to change, mutate our member variables. We saw that a couple of examples ago with that resize member function. Right? It changed the radius member of our circle class. If you can't remember, here it is again. Right, so we've got our circle struct, we've got a radius member, which I've forgotten to give a default initializer, but never mind. And then we've got this resize member function. What this is doing is it's mutating, changing the radius member. Everybody agreed on that? Yeah. But when we declare an object to be const, that's saying we can never change that object ever again after we've initialized it, after we've given it its initial values. That's it. We can never change that object ever again. So this is kind of a problem now, because member functions can mutate member variables, but there are some variables we can never change. So what's the result? The result is that we can't call member functions on a const objects. No, fortunately, this is not the resolution to this. The actual resolution is that if a member function does not mutate any member variables, then we have to explicitly mark it as being non-mutating. We have to say this is a read-only function. And the reason for that is because we don't want the compiler to have to go through and sort of analyze our function and decide for itself whether we are changing anything or not. That would be, not only would it be slow and difficult, it would actually be impossible in some situations. So we have to say right up front, okay, this is a read-only member function. We don't get step-by-step reveals on this one, never mind.
Quick question.
Yeah.
I didn't get a chance to test it, but what if the argument you're passing into the function, inside of the parentheses of the function, you said it was a const reference?
Yeah.
Still fail,
Yes.
even if you
Because
said that you're not going to change anything, it's going to be a const ref to the
you would still not be able to call, for example, the resize member. So to mark a member function as read-only, to say that, okay, this member function, I promise I am not going to change any of the member variables, we write the word const after the closing bracket, just there. So between the closing bracket of the parameter list and the opening brace of the actual body, we write the keyword const. Const, immutable, read-only. This is a promise, an indication that this function is read-only. This function does not mutate the circle. And if we have this marker on here, now the compiler will allow us to call this member function on a const instance of a circle. As we can see, right at the bottom for those who can see, I've declared a const circle. And now I'm going to call the getArea member function. And this is okay, because this circle object that I've created can never be changed. But getArea is saying, hey, I'm a read-only function. I don't change anything. I'm non-mutating. You can call me. It's fine. It's safe. That's allowed. Right, so when we first started talking about consts, I don't know, weeks ago, I said that C++, unlike a lot of other languages, C++ is really hot on what we call const correctness. Right? Marking when things cannot be changed. And this const, what we call qualifier, on member functions is a really vital part of that const correctness. I've somehow managed to not do the animations on these next couple of slides. Let me just fix that. So here's the key thing. When we mark a member function with this const annotation, this const qualifier, it's not just us promising. It's the compiler enforcing that we cannot change anything about the object, even if we wanted to, right? All of the member variables that we refer to behave as if they themselves had been declared const. It is a compile error if we attempt to mutate them, if we attempt to change them. So here's our friend circle again. This time I've added a second member variable. It's called getAreaCalled. And what this is going to do is, given our getArea function, this is just going to record whether anybody has called that function yet. So initially it's false. Within the function, the first time somebody calls that, we're going to set the variable to true. Or at least that's the intention. But this actually isn't going to work. And it's not going to work because when we mark a member function as const, the compiler, the language prevents us from making any changes to any of the member variables, even if we wanted to. Yeah.
Does that cascade then? So, for example, where you've got getArea and then you've got that where you assigned true to the getArea called. If it was like another member function called modify getArea called, and then try to assign it, will it then say, hang on a second, you try to do that through a different function which was marked as const, and so you can't actually do that?
Yeah. Yes, yes, absolutely. So I was going to come to that, and you've no. That's really good. So yes, we saw the previous example. Member functions can call other member functions. However, const member functions can only call other const member functions. Right? So we can try and do this. We can, if we try and do this, we are going to get a compile error. We're going to get a failure. The compiler is going to give us an error message, something along the lines of, you've tried to modify this member variable, but this is a const member function. What do you think you're doing? Go back and think about your life. Yeah.
Could you have another function with the same name without const?
Yes, you can. I'll talk more about that next week.
So we can override the constant.
You can have two member functions of the same name, one of which is const and one of which is non-const. But I don't want to go. It's a form of overloading, yeah. But let's wait. Let's leave that till next week, right? Not only because it's 2 minutes past 9 and I should have finished by now.
Good things come to people who wait.
Yeah. So this behavior is good, and it's what you want like 99.9% of the time. There is an escape hatch out of this. It is possible to mark certain member variables using this mutable keyword. And if a member variable is marked as mutable, it means you can mutate it even within a const member function. Right?
Would it be equivalent to unsafe in Rust?
No, not really. But it is something that you should do rarely. There are valid use cases for it, particularly if we ever get round to doing a module about multi-threaded programming. The mutable keyword becomes very useful there for handling locks and things. But in general, the mutable keyword is something that, it's one of those things that, of which there are many in C++. It's to kind of be aware that it exists and it's there in an emergency when you need it, but most of the time you probably should avoid it unless you kind of know what you're doing with it, I suppose. But I thought I'd mention it for completeness, that there is an escape hatch, but try and avoid using it most of the time. If you find that you need to use it, well, perhaps you've done things, your design is perhaps a bit wrong. So, I need to wrap up, unfortunately. I did have a second little exercise. It wasn't really an exercise, so much of an exercise. All I wanted you to do, really, and you can take photos of this if you like, is just to take that little one you just did with your equal to and not equal to, and just make those member functions read-only, which I'm sure won't take you very long.
By the way, can we get the download parts on
Yeah, so as I mentioned, I've been very slack and not, despite being nagged to do it, put up last week's slides yet, but I will do so. So yeah, you can have a go at that, and I will rapidly skip over my solution. One too many. Back you go. There we are. Right. There have been complaints that I am not working you hard enough, not, giving you enough to do. So this is 1, 2, 3, 4, 5, 6, 7, 8 or 9 bullet points worth of homework for you to really get your teeth into. Right? This is right. This is an exercise. I want you to write a tiny little, but a small kind of record-keeping app for, say, these sorts of classes, right? Something that records a list of students, a list of modules, and can associate a set of marks with the students and the modules. And, I sort of walk you through what to do at each step, right? So don't worry, I'm not just throwing you into it and saying, do this. I'll walk you through what I want you to do at each step to kind of build this up. And you're going to have to, obviously, define some of your own structs and your own member functions. I haven't mentioned const member functions, but, you can hopefully decide which member functions should be const and which should not be. Okay, so, yeah, we're well over time, so I really do have to wrap up. But, yes, I encourage...
All for next week.
Is it all for next week? I've been gentle with you so far. I got complaints that I was being slack. So I thought I'd up the level a little bit. No, obviously the homework. I'm not collecting it in and putting it on your permanent record. If and I appreciate people are busy, and if you don't have time, that's fair enough. But it's there if you want it. If you do have time, if you're going to come along to the Thursday workshop session, which I've just remembered I'll be taking this week because I completely forgotten, then we can work through this and have a go at it. And you'll probably find it's not quite as scary as it looks just when it's a wall of text on the screen. Right, so... Sorry? Oh no, I don't mean like an iPhone app. No, no, that's next week's homework. Come on, I'm not throwing you in at the deep end. Yeah. Anyway, that's it from me. I'm going to leave the homework on the screen. Thank you everybody for coming. Sorry for overrunning. Sorry for starting a bit late. But we're going out for a drink. Everyone is welcome to join us. Thank you very much.